Okay, so hey, I just wanted to show you give a presentation real quick here, give a video for review of just a simple linear regression model. Went over this a lot in class, not a lot, but a little bit. But anyway, I just wanted to get this up there to get some of these ideas in your head, and I'll post these slides too, so you guys can refer to them. All right, so the idea here, and let me just make this a little bigger so we can see it. Send that in. There we go. All right, so we're trying to establish this relationship between two variables. All right, so one way we can do that is with regression. All right, so the basic idea is to try and find, a functional, it says here, relationship of this equation, right? We're trying to predict y. We're going to manipulate y. We're going to take the average. We're going to put a little hat on top of it and call it y hat. All those things, but the idea is trying to predict y based off of x. I think you guys understand this, but it basically breaks down to us kind of doing, correlation between these two features. That's why the optimization function, this sum of squares error kind of function that we looked at, it's going to look a lot like the correlation function, that I showed you guys in class. So let's look at that function again, the simple linear regression one. Okay, so here again, we're trying to predict I. B is going to be our y-intercept. So that means it's going to be what y is when x is 0. Right? So it's basically starting at nothing. And then this is going to be our coefficient, right? That we want to try and figure out through the sum of squares error process. I showed you the closed form in class. It's a mathematical way to represent regression that you can do with dot products. But I'm going to show you the sum of squares error, which is a little bit more typical, and is actually the method that we would use if we wanted to optimize this in kind of more advanced ways that we'll talk about later in class. Okay, so the BI, here you think this B1, this beta 1, we're trying to figure out that's the slope of our line, and then x is just going to be whatever the inputs we're putting in there, right, to calculate this eventual y. So we add those together, and then the last part of it is just going to be the error variable. That's the average error associated with our prediction. So we want to add that in to know just how far off we are with any one prediction. All right. Okay. So again, this is the simple linear model here. All right. All right. So there's no. I showed you like a polynomial form, where there was like a square up here, right? We're not taking the exponential of anything. This is just straight linear prediction, right? Straight kind of the linear, that's kind of the idea of this linear line. All right. These are examples of kind of more advanced, kind of linear manipulations. All right. This one is non-linear because the exponential is on the beta. All right. But this is still like polynomial, still kind of a linear regression line. All right. These are kind of more advanced. We'll show some of these. We'll get into a little bit more of these, kind of later in the semester. But, this is not a linear relationship, basically because of the division, right? So what it's saying here is just adding all these features together, even if we manipulate them a little bit and kind of force it back in. The idea is that we add these together. This here, we're manipulating this based off of division. Okay. So this is the whole deal. This is it. Here this is our y-intercept. That's where we're starting at, right? And we're trying to determine the slope of this line, which is just the run over the rise, right? And I'm gonna walk you through how to calculate these using this sum of squares error method. All right. This is just it's an ugly chart. I'm sorry, I should have done a better job. But here, this is our estimate, and this is just one example of a regression line, and we're gonna build this out here in the next couple of slides. I'll show you how it works, but obviously we're just trying to fit this line right in between these points. Okay, and this is our slope basically of our line. This is our intercept of our line, and this is our slope here. All right, that we're trying to figure out. Okay, we also need, scatter point shows these points here, these points, but we want to try and figure out what the error is, because those points aren't exactly on the line, right? So the y is our response variable again. The x is the predictors, those are independents, right? And then epsilon are basically the error term, all right? This here, we're trying to figure that out. We have to assume the errors are normal. That means that they kind of like factor out to 0. And what that makes sense, right? If we look at all these errors, right, because we put this line here in the middle, if we added them all up, plus, minus, they should equal 0 based off of that line. So that's important. Okay. All right, so let's take a look at the equation that we're trying to minimize here. This is the least squares, all right, equation, which is one way to get a linear regression model, all right? So we're going to use that, all right? And the goal here is to minimize the y-intercept and the slope given b and y. We minimize because we want that to be, we want the error term to be as small as possible. So again, this is just what our, our equation looks like. And we're going to do it using this equation here. We're going to spin this out to make it make more sense as we walk through it, all right? And again, we do have these residuals. That's the difference between our predicted and the actual number, all right? And those are just going to be our error terms, all right? It's the same as the error we presented before. All right, I'm going to skip over these because they're just really ugly. And again, sorry about the font here, but it's kind of nice to contrast this. So this is the simple linear regression model, all right? And this is how we find the least squares regression line, all right, to include essentially in this model, right? So we want to estimate these things. So these components, they break down into these pieces here. So the B1 equation is this sum of squares, right? X and Y sum of squares divided by sum of squares of X, all right? So that's how we find our B1, all right? And BO is going to be the average Y minus, right, the coefficient multiplied by the average of X, all right? So that's a little tricky there, but basically the two pieces we need are these components here, the sum of squares X and the sum of squares XY, right? And you can see the equations are pretty straightforward here. If we break these apart, right, we're just subtracting X from the average, subtracting Y from the average, and then we're summing those together. Same here, we're just doing this, we're just subtracting X from the average and then squaring it, all right? And another way to look at that is just to do it with this equation here. So we're going to use each one of those as we build out our regression model. All right. Again, these are what our errors take, so we'll assume those. I'm going to show those a little bit, but I'm going to just jump in to an example here. Okay, so what we have here, right? So we're an economist, all right? He wants to know if there's a link between income and education. So these are random sample. We got 10 people here, okay? All right, and ask for their income, in the thousands, and education in years, all right? So that's what we got down here below. All right, so if you want to, you can pause right here and say to yourself, all right, which one is the Y and which one is the X, all right? So take a look at this question. An educational economist wants to know if there's a relationship between individuals' income and education, all right? Yeah, I mean, maybe it's easy if you didn't pause, it's fine, all right? But education is going to be the independent while income is going to be the dependent, right? We're trying to predict income based off of education. All right. So dependent variable is the one that wants to forecast or analyze, right? So that's the one we're trying to forecast. In this example, income, all right? So we want to analyze income. So we chose an individual's education and see how that affects income. X, Y will be our predicting, it's going to be our income, and X is going to be our education, all right? So the first thing we need to do is basically break these the equation I showed you a couple slides earlier, into a bunch of different pieces that we can use, all right, to just do these calculations, all right? Now again, the one we showed in class with the inner products, that's a closed form. This is a way to do it and using the sum of squares, basically the least squares method. And this is the one that's a little bit more common, but that one is also super efficient. And I can talk about the difference of those in class, all right? So here we just have all the features associated with education and income, all right? And we're just going to calculate all these different components that we need, all right? We need a sum, all right, of X. That's just adding all this up. So education, thank you, we got it, 118. We're going to take the square, but it's the square of each one of these. So I actually have that down here, right here. So you take the square of 11 is 121. You add that all up, and you get 1,450. If you do the same thing for Y, we add all the Y's together, okay, all the incomes. We will square them, which is what is down here on this row, all right? And we add it all together, we get this, okay? And then if we add these two together, all right, the two square components, this is what we get here, okay? All right, oh, I'm sorry, if we multiply those two together, right? Not the square components, my apologies. We multiply these two together and then sum those. This is the total that we get, 3,779, all right? So we're going to use each one of those in this next slide here to basically calculate the components, our y-intercept and our coefficient, our beta 1. So we're just kind of plugging and chugging here, all right? So remember this SSX, right? All right. So we need that to help us calculate all right, our intercept and our exponential value. So we're going to do that, and that again is the equation we showed up here, just to bring it back. All right, so we have this sx here, ssxy, which is going to be a part of this beta 1 here. All right, and then actually I guess we don't need it for our y-intercept. All right, so it's not there for that one. All right, but we're going to use it to calculate here for our coefficient value. All right, so we're just plugging that in. All right, and it comes out with 215. All right, we do the same thing. We need this sum of squares x. We're going to do the same thing. All right, just basically plugging in these numbers. All right, and then we can use it right down here to calculate our b1 and our intercept. All right, so b1 is just these two numbers divided by each other, so it's 3.74. So that's going to be our coefficient value that we multiply by x. We take the average of y. All right, we're going to subtract that by our coefficient value, right, times the average of x. All right, so to get to b1, all right, we're going to take 302 here and put that over 10. And we're going to subtract that by 3.74, which is our value here. And then that gets divided by 118 over 10 again. So 10 again is our n. And then if I go back up here, just so you guys can see it. All right, 302 is the total for y. Okay, so that's what we're putting in there. All right, that's what 302 goes right here. All right. Okay, so let's keep going. All right, that's the average, right? That gives us the average of y times the coefficient times the average of x, which again is that 118 divided by 10. Okay, so we basically built our regression equation here. Okay, so this is what it's going to look like. All right, if we were to estimate y, that negative 13.93, right, is our outcome value here for our y-intercept. Okay, and then 3.74 again is our estimate here for our coefficient value. And so we built the equation. So if we're moving forward, we wanted to estimate certain values based off of education as it relates to income. We just put in education levels here, right? You know, whether that's 10 or 11 or 12, whatever that might be that we showed up here, or maybe it's more. I mean, this person has a PhD, they're in school for a long time, right? And that would give us our estimate of those values. Okay, so that's basically at the core, and that's what it says here. The sample slope is this. That's our rise over run. It tells us the average for each additional year of education an individual's income rises, all right, by $3,000.74. All right, so that's the way to think about this, right? For every unit increase in education, a unit increase for education is in ones, right? It goes up by ones here. We get the multiple increase of $3.74 thousand, all right, in income, right? It doesn't account for everything, of course. We have to check out to see how much error we have in these estimates, and that's the next step where we do kind of this average mean squared error, where we're calculating our epsilon here, which is our error value. We do that by calculating the total sum of squares error, right? And then we can take the average of it, which is what this looks like. Again, this, I'm going to go back to the slides, but it's just plugging and chugging here. We're taking y, which is our total value of y. We're squaring it. We're dividing it by 10, all right? And we're subtracting that by the sum of squares value. All right, so that gives us our sum of squares of y. We do the same thing for the sum of squares of x. It's a lot of sum of squares. All right, and then to get the sum of squares error, all right, we just divide that total squared error of x and y, which is over here, all right? And we divide that by our squared of x times x, all right? And that gives us our sum of squares error here. And then we're just going to use these numbers to calculate and take the square root of to put it back in terms of the target variable, our total kind of squared error. You can think of this as the root mean squared error. So what this is saying is that for every estimate that we're off of 3,000, we might actually be off by about 4,000. Okay, so this error totally encompasses kind of our estimate of our coefficient, which isn't super great. We can take a look at the total range of our y values and get an idea about how much of error actually this represents. So if we went all the way back, I guess, I don't know if I mentioned that down here. All right, so like our average is 30.2. Okay, so it's actually not that bad. All right. So we think about the total average for income. This is our average income estimation. We're only off, when you think about the average in terms of the total income we have, only off by about 4,000 per estimate. Still not great, all right, but it's not totally bad. So we can conclude that S is kind of small, indicating that the regression line actually fits the data pretty well. And we kind of bear it out, when we looked at this sample information up here when we were kind of playing around with this. We got an idea that it looked like it was going to be pretty close, right, with our sample information, because that line and the dots are pretty close to that line. Okay. So I hope that helps. I'm going to stop right there. What we're going to do is I'll go over this. I'll post this up and send it out. Many of you probably won't have a chance to look at it right before class, but if you do, I'll ask you questions. I'll go through it again really quick at the beginning of class, and then we'll go through another kind of applied example just to get your arms around this. Okay, thanks so much.